Did I not? Okay, sorry if I forgot to, but I think it presses now. All right, anyway, so let's go back. So miss few minutes now. Okay, let me go back to the slides. Yeah, perhaps I forgot to press, or I didn't press the final button there. Right, thanks for reminding. Okay, yeah, so we melt the silicon in the crucible at high temperature. So at 1400 degrees C, so it's going to be melted. Then what we're going to do next is we put a seed of silicon with a specific orientation. So let's say if you want to grow 100 silicon, then your seed is going to be 100 there up here. The seed up here, right? The seed is going to be 100. So then the seed is going to be slowly pulled. Slowly dia akan diangkat slowly at certain rate, and then we're going to have rotation as well of the ingot coming out from the melt. So the ingot is going to end up following the crystal rotation of the seed. So if we dip 100, then the whole ingot that we grow is going to be 100 oriented as well. So the whole wafers within the ingot before the cut is going to be 100 oriented according to the seed. Okay, so the seed is going to be oriented, counter rotated. So the speed and the rotation, everything is going to be monitored, right? Then dopants are added into the melt at the start of the growth. So if you want to grow P-type silicon, then we're gonna need to include boron. Well, normally boron into the melt at certain level that you end up with certain doping level on the wafer. So, well, usually we've learned last time in intrinsics that you can go from lightly doped, or in fact, you can go undoped intrinsic. You can go lightly doped, you can do moderately doped, you can go heavily doped, according to what you want to achieve in your materials or in your devices. So if you want to grow N-type, then you're going to need to incorporate phosphorus into the melt, and then do this very same thing, pull, control process. Then we're going to end up with N-type silicon. So it's worth to note that during the growth, we're going to end up with oxygen in the silicon ingot up to about 10 to the power of 18 centimeter minus 3 per centimeter cube, due to the incorporation of oxygen into the melt during the growth process. So it's going to end up in the silicon, right? So we want to minimize the incorporation of oxygen into the silicon wafers or into the silicon ingots up to this level. We don't want to go higher. If you're going to go higher, then it will probably change the electrical properties of the silicon. So another process is called MCZAC. The first one is now was CZAC or Czochralski, and the second one here is called Czochralski process as well, but with magnetic field. So you can see the magnetic field is impacting the growth process. So the magnetic field is applied by the frame of the crucible. Okay, so it's called magnetic field applied CZAC or MCZAC. So carried out within a strong horizontal or vertical magnetic field. So what it does is that it controls the convection of fluid or the melt in order to minimize mixing between liquid at the center. Liquid means liquid of silicon, the melted silicon, in the center of the bath with the one at the edge. So the one at the edge, bila you ada crucible, macam kolam, so the one at the edge normally they are the impurities because you use it many times, and then there'll be out diffusion of certain materials from the walls into the melt, and then these will be unintended impurities in the silicon ingot. So we want to minimize that by having MCZAC. So it will create a liquid silicon crucible around central silicon bath. So it will also help to trap oxygen and slows its migration into the crystal. So thereby we're going to end up with lower incorporation of oxygen in the melt. So lower oxygen concentration can be obtained and impurity distribution will be more homogeneous. So with this, we can reduce the oxygen concentration to the 17, so 1 order of magnitude lower in comparison to ZAT process without magnetic field. And also the carbon concentration below than 216. Carbon is actually coming from the crucible itself. Okay. So MCZAC is overcoming the weakness of CZAC process. So this is how the configuration looks like in the CZAC process. So you have seed up here, and then you have a puller there. This is your seed, either 100 or 111, or whatever you like. So this will be your ingot, right? It's going to be slowly pulled. So the below here is the melt. Macam lava, but you melt the silicon high temperature, then slowly slowly pull out, and then what's actually happening is that the liquid melt will cool down when it's pulled out, because it's no longer within 1400 degrees C ambient, and then the cooling process leads to crystallization. Dulu pernah belajar crystallization process. Apa maksud crystallization? Ada belajar ke material science? Did you learn this in material science or other subjects? Crystallization. Have you ever come across the word crystallization? Belajar ke? Anyone? Syami pernah belajar? Crystallization. Have you come across crystallization anywhere in physics? Ada? Anyone? Don't remember? So apa crystallization? Crystallization is the what we call the process which changes the properties of material from liquid, if you like, or amorphous, if you like. Kalau kita assume the what we call the liquid melt is amorphous, and then it's going to slow down, it's going to be cooled down, and then it will crystallize. Dia akan crystallize, dia akan form crystal orientation. Maksudnya dalam melt tu dia belum ada lagi, sebab there's no reference to begin with. Bila kita ada seed yang jadi reference, so dia akan grow on the seed following the seed punya orientation. So then it will be crystallization process on the seed, following the seed. So maksudnya apa yang kita grow tu will exactly copy paste lah, if you like, copy paste the properties of the seed, right? So it will crystallize, and then it will form single crystal. So by this process, so the aim is to produce single crystal silicon p-type or n-type according to our desired orientation. Molten silicon is in there, then the heat shield, the carbon as the heating element, so that's where you get the carbon into the melt as well, so it has to be controlled. We don't want carbon to be part of the silicon wafers, but somehow it's there, but under control concentration. Right, water jacket is there to do the cooling process so that you can actually regulate the temperature of the CZAC system or the crystal cooler. So this is a representation of what's actually happening during the process. Kalau nak clearly, you can just go to the video later on, see the watch the CZAC process punya video, short video. So exactly like what I've explained is now, it involves melting from the first step, melting of the silicon chunks, introduction of the seeds, and then slowly pull, and then control the rotation and everything, and then kita akan end up with an ingot following the exact orientation of the seed. Okay, so that ingot will then be cut into wafers. Then kita akan pakai wafer to do the fabrication process. So this is another representation of process. Polysilicon chunks on the top in the graphite or carbon crucible, melting process, cooling process, and then you're going to end up with the ingot. Yeah, that's how it looks like. Another representation on the left, and the final ingot on the right. So you can see there. So look at the height or the length of the ingot. So if the man or the lady's height is, I don't know, 1.8, maybe the ingot is somewhere 2 meters in length. Yeah. So yeah, so it varies according to the power plant that we have to do the growth process. So it can be shorter, it can be longer, right? According to the design. So right, you can go to the YouTube here to watch. So this is how it looks like in the production line of silicon ingot factory. So if you talk about industry punya scenario, usually ingot punya factory ni is part of the wafer fab. Maksudnya kalau you do all the integrated circuit fabrication in one particular company, then usually the ingot growth is done by somebody else. So maksudnya dia punya supply chain tu, there'll be ingot growth company as your supplier, and then kalau you one of the QA engineers in a wafer fab, then you'll probably be looking at the quality of the incoming wafers from one supplier who fabricates the silicon wafers. So they do the ingot growth, and then they produce the bare silicon wafers, 8-inch or 12-inch or 18-inch, depending on type of wafer fab that we are. Then we examine the properties of the quality of the wafers, and then we buy the wafers. So kita jadi customer dia lah, kita jadi customer dia, dia jadi supplier kita. Then we're gonna do the fabrication, then we're gonna finish the fabrication, then back end will be our customer. So kita akan jadi supplier kepada dia pula. So you can relate this to the EE value chain that I've shown you before this. So how does the value chain looks like from the front end, the beginning of the front end, to the final assembly and products punya line. Okay, so hardly ingot growth ni is under one roof, but I know for one solar company, it's called Longi in Sarawak. They do everything together under one roof. So that means they grow their own silicon ingot, and then they cut their own silicon wafers, and then they fabricate solar cell on their own silicon wafers, and then they from the completed cells they fabricate they produce the module, silicon module, solar panel yang besar tu 1 times 1.6 meters on their own. So they do everything from on their own from the first to the final products. So, and this is a rare case. If you look at solar cell industry, typically the wafers are supplied by somebody else, and then you do the fabrication, and then some companies actually do the solar panel assembly themselves. Some other companies do, for example, ada company kat, if I'm not mistaken, JA Solar, they buat solar cell fabrication in Bayan Lepas, but then the panel itself is assembled in Vietnam, if I'm not mistaken. So they actually ship the completed solar cell wafers to somewhere else, to even other countries, and then the assembly is done by the plant in other countries. So macam Jinko Solar kat sini, they do everything themselves. They fabricate the cell, they fabricate the module themselves, and then the module is ready here under one roof. So it really varies across the industry, and in fact, manufacturer to manufacturer put out different preferences. So there's no one size fits all kind of thing, even when you talk about manufacturing. Right, ready silicon ingot, you can see horizontally laid there. So macam tu dah siap tu. So they are all ingots, I don't know, possibly 8-inch or 12-inch. So you're not going to use the bahagian bucu tu, you're not going to use this part. It's going to be cut like this anyway, like that. And then we're going to cut according to the thickness that we want for our fabrication process. Right, CZAC silicon is called ingot or bowl, but most commonly called ingots. Typical length is 1 to 2 meters. It ranges from manufacturer to manufacturer, industry to industry. So it'll be sliced into smaller circular pieces called wafers. Yeah, for wafer fab, we normally use circular shape. it's either commonly used is a 8-inch or 12-inch or 18-inch, so which refers to 200 mm or 300 mm or 450 mm. Okay. Thickness for the wafer fab is typically around 500 micron. If you talk about solar industry, it's usually 180 micron for now. So about solar industry, the benchmark is different. For integrated circuit, the benchmark is different. Transistor operation, high speed, blah blah. The output parameters are different. When you talk about solar cell, for comparison, solar cell, the benchmark is dollar per watt, right? If you so the benchmark is different, dollar USD per watt. Ini kalau solar industry lah, just for comparison. So that means this is referring to technology cost. So how much USD you pump into the manufacturing process over how much power you can extract from the cell, from the huge panel. So it's called dollar per watt. So in order for you to minimize the dollar, to reduce the dollar, because you want to reduce the dollar per watt so that the technology becomes more affordable to the world, right? To the B40, to the world, in fact, rich people as well. You want to reduce the dollar pump into the manufacturing. And one way to do that is by reducing the thickness of the silicon wafers. So you can't afford to use 500 micron of silicon wafers for solar cell production line. Okay, so that's why the current 180 micron. And in fact, the industry is going for thinner and thinner and thinner wafers in order to minimize the dollar involved in the manufacturing. But it comes with another drawback. Well, typically, we've learned this one last time, 386. When you reduce the volume of material for your solar cell, you will reduce the interaction of the light with the volume, so therefore you will reduce the current as well. So therefore, you need to have some optical strategies to make sure that the current is retained even though you're going for thinner wafers. Naim, right? MCZ, does it mean impurities more homogeneous? Oh, okay. What it means is that you can actually minimize impurities coming to the central area of the bath or of the melt, because the central area will be the main area you want to work on your device, right? So the edge will be, the secondary area, if you like. So if you can minimize or you can control the migration of the impurities from the crucible into the bath, or you can just make sure they are just on the edge of the ingots but not in the central area, then you can actually minimize impurities in your active area of the device later on, because the main device will be fabricated in the central region of the ingots. You'll see later on, right? So this means that you can to some extent control the homogeneity of the distribution of impurities within the whole ingot. Okay, so each wafer here will make millions or billions of transistors. You've seen yesterday when we talked about Kirin 990s, tens or billions of 10 billions of transistors in the area, right? Okay, distribution of dopant. So we have discussed that you can, when you do the growth, you can either leave it intrinsic, which means undoped, or you can introduce extrinsic impurities like what we discussed in 386 last time. So extrinsic, masih ingat lagi apa? Kita incorporate dopant kan? Extrinsic means two, so it can mean undesired impurities like metals, copper, iron, whatnot. That's not desired in the device, in the active area. But we can also incorporate desired impurities like dopants in this case. So you can make your wafer p-type by incorporation of boron. You can you can make your wafer n-type by incorporation of phosphorus. So these are the common dopants. On the other hand, you can also use some other dopants like gallium, like aluminium for p-type, or arsenic, antimony for n-type. But if you talk about the common ones, the p-type is usually made by boron and n-type is usually made by phosphorus. So they belong to group 3 and 5 on the periodic table. So silicon is group 4, is the host. So you have to understand, you've got the basic understanding of how does doping works, right? Remember the four neighboring bonds of silicon. When you put on phosphorus into the lattice, and you're going to end up with one free electrons wandering across the lattice and giving conduction. And on the other hand, if you put boron in, you're going to lack one bond, so that will be a vacancy or a hole. So it will also wander across the lattice, giving p-type conduction. Okay, how are they distributed in the melt, the dopants? So the way the dopants are incorporated into the crystal depends on segregation coefficient. So it's called segregation coefficient, or K naught. So what this essentially means is whatever you put into the melt doesn't end up in the ingot. Okay, maksudnya kalau you put 100%, tak semestinya 100% tu akan masuk dalam ingot due to some properties, right? So it's called segregation coefficient, and it's given by CS over CL. CS is concentration of dopants in the solid form, so that means in the ingot, over concentration of the dopants in the liquid form. So maksudnya apa yang you end up in the ingot over what do you actually put in the melt during the process. So the value of K naught is less than 1 because of the solubility of impurities of dopants, in this case phosphorus or borons, is larger in the melt than in the solid. So because of the solubility of impurities is larger in the melt than in the solid, so you're going to end up with lesser dopants in the solid versus dopants in the melt. So that will give you perhaps 0.8, 0.7. Okay, so this also means that crystallization is also a purification process. So you're going to end up with the highest, somewhere 80% of the concentration in the ingot. Impurities will become concentrated in the part of the crystal last crystallized. So bila you pull and the dopant is being incorporated during the pull, so dia akan macam berkumpul kat ujung lah. Ujung tu kita akan potong ni, because you don't want to have different distribution of dopant across the ingot. Kita nak dia uniform across. Okay. Kalau you dapat ingot yang tak uniform in terms of the doping level across the ingot, apa implication ya? Kalau you grow 2 meters of ingot and then the top parts of an ingot have I don't know, maybe 10 to the 18 of dopants, and then the lower part has, I don't know, 10, 19. So is it okay? Is it okay to grow like that? You grow 2 meter, 1.5 meter is 10, 18, and then another 0.5 is 10, 19. Is it okay or not? No, yes, no, inconsistent. So if it's inconsistent, what does it mean? So kalau tak consistent, apa implication ni? What do you think is the implication? Kalau you jual ingot ke orang, how do you sell the ingot? Can you sell the ingot? Will they buy from you? Kalau you buat kek belah kiri terlebih gula, belah kanan kurang gula lah. Yeah, less quality lah overall. Kalau you masak certain part, you buat cake dah crystallize kan, solid form ni. One part tastes different and another part tastes different. So you'll probably sell one time. Second time no more. Okay. Sama juga when you talk about inhomogeneity of dopant distribution across ingot. So the implication means kita dah belajar dulu when you talk about doping level. So if you incorporate 10, 17, or 18, or 19, it has to be consistent across the ingot, because whatever you have as your doping level will actually reflect the resistivity of the wafer. Right? You have to go back to the resistivity doping level versus resistivity curve, or the other way around, versus doping level curve. Hari tu kita tengok dalam kelas last time. I think I did ask 1 ohm cm equal to how much in terms of doping level, right? And the answer is like 1.5 E16 or something. So So you want to control that. Kalau you punya ingot tu 2 meters, then your resistivity is everywhere. You don't really know how the distribution is. Then you cannot sell. So this is happening to n-type because we'll see why later on. The dopant distribution is not so uniform, and then the manufacturers usually end up cannot sell the whole ingot. So they grow like 2 meters, they probably can sell 1.8 meters, and another 0.2 meters need to be remelted and then regrown into a new ingot. So maksudnya you fabricate, you buat ingot 100%, then you can perhaps sell 70%, 80%, and the other 20% or 30% is lost, not sold. Okay. The distribution of impurities includes doping level. Doping elements and oxygen will change along the length of crystal. Therefore, homogeneous doping is difficult to achieve. We want to be as homogeneous as possible. And for us to be high in homogeneity, we need to use dopants with high K0 value. So kalau you pakai high K0 value, approaching 1, then you'll probably end up with better homogeneity across the ingot. So if you look at this, cuba tengok boron. So what's the value of boron there? Boron is 0.8 to make p-type. So that means, apa maksud 0.8 here? If you go back to the equation there, so boron K0 is 0.8. So that means if you put 1 in the melt, so you're going to end up with 0.8 of boron, whatever the unit is, in the ingot. Maksudnya 20% is not incorporated and 80% is incorporated. So that's what it means by 0.8 here. All right, in contrast, look at phosphorus. Phosphorus is 0.35, which is better or worse than boron? If you look at the value, is phosphorus better or worse than boron? Worse, right? 0.35. So that means whatever you put in, if you put in 1 of phosphorus, whatever the unit is, you're going to end up with 0.35 of 1 in the ingot. So much the remaining are not incorporated. So that's what it means by segregation coefficient. Okay. Segregation coefficient also depend on growth rate. So it's not a fixed value though. So it depends on the growth rate. But normally when you want to compare the segregation coefficient of 2 different dopant atoms, it has to be compared at the same growth rate. So then only you can see the difference more clearly. So the implication is that if you have high, since you have high for boron, 0.8, and lower for phosphorus, so normally manufacturers will face difficulty of growing uniform resistivity across n-type ingot because the K0 is lower. So they end up not able to sell some parts of the ingot, even though they've grown the whole, the whole length of the ingot, because it's not so uniform. Because the distribution of the resistivity across the ingot is not as good as boron. Okay. All right. Crystal silicon ingot grown from silicon melt in silicon crucible. A few silica that the chamber itself react with the hot silicon. This is how oxygen end up in the silicon melt to produce 10 to the 18 of atoms per cm cube. Okay, try to calculate this for yourself. We'll probably discuss today. This is on the K0, and right, you have to look at the boron or phosphorus. So what's actually the amount of the boron or phosphorus need to be put into the melt in order to yield certain level of concentration in the ingot. Right, go back to the equation as K0 is now. So yeah, I think I'll just stop here on the process. We're gonna look at float zone next week. And then we're gonna look at the comparison between FZAC and TZAC process as well after we've covered the float zone process. Yep. try to do the calculation first, and then on Monday I'll probably call you to share your calculation on the screen, and then you can share your content, and then we discuss. Okay. Right then, that's it for today. Any questions? All good so far. 11:50. Can you all follow so far? So far, so good, right? So the growth of silicon is not that complicated. So it will be more complicated when we talk about fabrication itself. Alignment, removal of certain areas, and deposition. That will be more complicated. So far, so good. All right then. No questions. Okay. So semua okay. So, yep, that's it for today. Then I'll see you Monday. Hari Senin, minggu depan kita punya jadual ikut jadual baru So we're not gonna have a class on Wednesday, right? So there'll be classes on other days except Wednesday. Saya dah update dalam course introduction yang updated tu. You can see the slide and it's the updated version. Okay, that's it for today. That's all. Thank you very much. Take care. Bye-bye. Assalamualaikum. Have a nice weekend, you too.